So now we've looked at operating systems and what they are, let's have a look at the type of job that they do. And there's a number of different jobs that they do. The components and the jobs span the whole, because it's just so much work to do when you imagine how many programs might be running on your computer. In the old days, we didn't used to run so much stuff because it was slow and clunky. These days, as you know, you can be opening a browser, you could have a word processor, you could be doing something on a spreadsheet, and you can be playing a game at the same time because our computers can handle it. And the job of the operating system is to manage all these things. So we're going to have a look at things like the kernel, exactly what it is, how it deals with program execution, interrupts, what they are, how memory is managed, what is virtual memory, what multitasking is, how we access the disk access and the file management, a quick look at device drivers. We'll have a look at networking, which is ever so important these days with the internet. And then with that, along with that, security. Then we'll talk about user interfaces, and finally we'll end up with a graphical user interface. So I'll try and keep it simple and try not to go into too much detail. And I've got some notes that you can refer to and look at another time. So the first thing to talk about is the kernel. The kernel, not kernel as in the army kernel, but I guess, you know, you could almost say that because that's basically what it does. It manages everything. It provides the most basic level of control over all of the computer's hardware devices. And it uses things like firmware and device drivers. Firmware, which is a bit hardware, and software, like device drivers. So basically the kernel sits on top of all the different things that we work with. It talks to the CPU, it talks to the memory, and it looks at all the devices that we're working with. And that communicates with the applications and then knows how to deal with those applications according to all those things as well. So it manages memory access for the programs in RAM, random access memory. It determines which programs get access to which hardware resources. It sets and resets the CPU's operating system state for optimal operations at all times. And it organises the data for long-term, non-volatile storage with file systems, things like disks, tapes, flash memories, etc. So it has a big job to do, and we're going to have a look at some of those roles that it plays as we go on. So let's talk about program execution. So the operating system provides an interface between the application program and the computer hardware, as we saw earlier on. And the application program interacts with the hardware only through the operating system and only by obeying certain rules and procedures that are programmed into the operating system. We've got to keep some order somehow. So we have a set of services which simplify the development and execution of application programs. So basically, when we execute a program, it involves the creation of the process by the operating system. So something's got to start the process off. We then got to assign memory space to it and maybe some other resources that it's going to use, and then establish the priority of it in a multitasking system, because there might be other things going on and we can't let one thing just hog the whole of the processor. We have to give everything a bit of time, as we'll see later on. And then it initiates the execution of the application program, which then interacts with the user and the hardware. So it deals with the program execution in a lot of different ways. And a lot of the key things here are interrupts. And these are centrals to the way the operating system works. It's an efficient way for the operating system to interact and react to its environment. You know, the alternative to something like that is for the operating system to sit there and say, right, you go now, okay, you have a go, and then wait until that bit finishes. And then it say, right, okay, you go next, and then just wait until that finishes. Or, you know, something like polling and just checking in with what's going on. You know, it's very unusual in modern operating systems because it could cause a lot of problems. If we give the ability of one process to hog the whole place, if it's a malicious piece of code or a malicious process, it could damage the system. So what we use now is something quite different. So what happens is it actually interrupts. So it will check on things as they're going along. And if there's any interrupts going on, it will deal with them. And it can interrupt things itself. So basically what it can do is it can say, okay, You've had your go now, and I'm going to interrupt you, and I'm going to save all the details in that particular context and any specific code, and I know where you've got to, and then go off and let something else run the process. And then eventually come back to it again with all the state still there and allow it to carry on processing. We have things like hardware interrupts. So if I want to save something to a machine, to a disk, then obviously we've got to interrupt a process to be able to save certain information to that machine. And sometimes hardware will interrupt the system to say, hold on, this didn't work, or hold on, this job's done. And it's supported by even the most basic computers. And basically it allows the program to specify code which can be run when events take place. This is part of the idea of a graphical user interface. If I click a button, then obviously there must be some sort of interrupt, otherwise the CPU will never get the instructions or never know that you click that button. So computers' hardware automatically suspends whatever program is currently running. Okay, so we have some sort of computer hardware that might say, right, you need to know about this. And basically the state will be saved, and the computer code that was previously associated with the interrupt is then bookmarked, just like you'll put a bookmarker in a book when a phone call goes and you put it down and you go and answer the phone. It's the same type of principle. And it's handled from the kernel, that it might come from the computer hardware or the running program that could cause this interrupt. Now, if a program wishes additional resources, then one of the ways to do it might want to get rid of resources. Then it might need a bit more memory, so it will trigger an interrupt to get the kernel's attention. So there's all of these things going on all the time. Interrupts, looking for attention, and the kernel then deciding who to give the attention to and who not to give the attention to. So there's a lot of work going on here. So when a hardware device triggers an interrupt, the kernel decides how to deal with it. It generally runs some sort of processing code, but the amount of code depends on the priority that that process has, because all processes have a set priority. And a hardware interrupt is usually processed by either a device driver, part of the operating system's kernel, part of another program, or both together. And then device drivers may then relay the information to a running program by different means. So there's a lot of different pieces of communication going there. A program may also trigger an interrupt to an operating system. As we spoke earlier, if I click a button, I'm interrupting the program because I'm making a choice. I'm asking to do something. So if a program wishes to access hardware, for example, it might interrupt the operating system's kernel, which then causes the control to be passed back to the kernel, and then the kernel then processes that particular request. So it's doing quite a lot of jobs, and interrupts are a key part to what's going on in a computer. And we can see here, in the diagram, that if you have the amount of time, you have a user mode, we have external events, and we have two processes there. And we've got our exception handlers or interrupt handlers going on there. So we're executing a process, and then we have an exception. Something goes wrong. Maybe the user types in something that's not understood. And what happens is that interrupt is then sent into the kernel. And for example, we might have an external event for a button being clicked. So that's an interrupt. So we can see that then this information goes into the exception handler or the interrupt handler part of the kernel, which decides how we're going to work with this, and then it'll come out of the kernel and say, okay, next process, you can have a go, and you can start doing the bits that you've got to process now because we've had this interrupt. So that's an example of how an interrupt might work. So the other thing a kernel and an operating system may do is deal with memory management. And when you have many resources competing, many processes competing for limited resources, this is quite an important thing to be done. We have to manage that memory because, of course, all processes want memory. That's their lifeblood and how they work. And the operating system manages all the system memory that's currently in use by the program. It makes sure the program does not interfere with memory that's already in use by another program. Otherwise, you'd have all sorts of conflicting things going on. So programs time share so that each program has an independent access to the memory. Because every program gets a slice of time, as we're seeing multitasking later on. And each program must have independent access to that memory. So we have, in the early days, we used to have things called cooperative memory management. Yes, you can see a problem coming up here, and it was used by many early operating systems and basically assumes that all programs make voluntary use of the kernel's memory manager and don't exceed their allocated memory. This didn't really happen, and it's almost never seen anymore because programs often contain bugs which can cause them to exceed their allocated memory. And in fact, that's one of the things that a lot of hackers will look for when they're looking for things like buffer overflows and trying to get into a system by looking for things like that. Program failure can cause a memory that's used by one or many other programs to be affected or overwritten. And malicious programs, you said just now, or viruses can purposely alter another program's memory or might affect the operation of the operating system itself. So once they're in and they can actually work with the operating system, and one misbehaved program can actually crash the whole system. So this cooperative memory management didn't work so much, and you won't see that anymore now. What we have is this protection, memory protection. And how does a kernel do it? Well, it's lots of different ways. We have things called memory segmentation. So it segments the memory that different applications are using. And we also do things like paging. So we can page information from memory in and out of the RAM, and we can work with that. Protected mode registers and it specifies to the CPU the memory addresses it should allow to run programs and memory addresses that it shouldn't allow to run programs. If there are any attempts to access other addresses, it will trigger an interrupt which causes the CPU to enter into supervisor mode and puts the kernel in charge, as we saw earlier on. And a segmentation violation, or a SegV for short, is probably something you've seen but you didn't realise. And it's usually a sign of misbehaving program, and the kernel generally resorts to terminating the offending program and report the error. And this could end up in a crash, or what used to be like the blue screen of death. In Windows 3.1, we had some sort of level of protection, but it could easily be circumvented, and a general protection fault would be produced, indicating a segmentation violation had occurred, and then the whole thing would crash anyway, leaving users with a blue screen, commonly known as the blue screen of death. So here we go, an example of memory management. We've got two executing processes, and we have them talking to the kernel, and as you can see, the kernel will then assign certain parts of the memory to those two processes, and they will have their own parts of memory that they can work in, and the memory operating system will actually deal with that. So what do we mean by virtual memory? And our virtual memory is memory which is accessed less, it deals with memory that's accessed less frequently for temporary storage. And it allows us to store information on a disk or other media so we can make space available for other programs. And that's why if you increase the RAM on a computer, it can help your computer go a lot faster, because virtual memory would generally tend to be used when we're running short of random access space. And what will happen is the operating system will swap different data that's in a particular part of memory, swap it out of random access and onto the disk. And then when the user requires it or the application requires it again, swapping that information back into RAM again. And it can be used by multiple, we can swap certain parts of memory that's used by multiple programs, so we can exchange it and swap it in demand. Now, if you remember when we spoke about speeds and relative speeds, well, we know that access to hard disk or external storage can be very, very much slower than access to RAM. So when we do this, we have to ensure that we can still keep the program running. So if you've got something like 500 or 600 page document, when you're on page 1, well, you're not going to want page 500. So, the computer will make the decisions, the operating system will make decisions on that to actually take that information and swap it out until such time that you need it. And what this does, it provides a perception that there's a larger amount of random access memory than the computer really has, but it allows us to be efficient. When we've got things like virtual memory addressing, such as paging or segmentation, the kernel can choose what memory each program may use at a given time. And it allows the operating system to use the same memory locations for multiple tasks, and so they don't all clash. If a program tries to access memory that isn't in its current range of accessible memory, but it's been allocated to it, then the kernel is interrupted in the same way as if a program was exceed its memory, allocated memory. Under Unix, this kind of interrupt is referred to as a page fault. So what does the kernel do when it detects a page fault? Well, it adjusts the virtual memory range of the program that triggered it, granting it access to the memory requested, as long as somebody else is not using it. And the kernel has this discretionary power over where a particular application's memory is stored, or even whether or not it has actually been allocated that particular memory. So the kernel is in charge. The kernel of the operating system is in charge of what's going on and keeps track of what's happening in the particular memory and the processes. So if we have a look here, we can see that we've got processes going along there, and we've got page 1, page 2 of the process, and then we can swap memory in. We've got a memory map, so the kernel knows how we map the random access memory and where we've mapped it onto the physical memory, either RAM or on disk storage, and then it can use this map to decide and to move things around and to know what's being used. So the memory is mapped, so we know what's in RAM, what's on disk storage, and then the kernel can decide how to bring these in. So now we move on to another important job of the kernel and the operating system, and that is multitasking. As we mentioned earlier, there are so many applications that can be running. We can be running a game, we can be doing a word processor, we can be on the internet, we can be doing all sorts of things going on, because systems these days support many different processes. And when we've got multiple independent computer programs running on the same computer, we want to make sure that everything runs. So what happens is the operating system gives it the appearance that it's performing the tasks at the same time. So it looks like it's being processed concurrently, but that's not actually what's going on. Behind the scenes, we actually have time sharing or time slicing. So each program uses a share of the computer's time to actually execute. And we have something called the scheduler, which is in charge of these things, and it determines how much time each process spends executing and in which order execution control can be passed to programs. And as we said before, in the early days we had this early model called cooperative multitasking. And yes, you can understand that what happens there is a program tends to hog the whole thing. So the program is allowed to operate and execute for as long as it wants before explicitly returning control back to the kernel. But as we mentioned earlier on, if we have a malicious or malfunctioning program, it might not only prevent other programs from using the CPU, but it can hang the entire system, and it can also create something called an infinite loop. So this wasn't the best way of doing things. So that changed. So modern systems now, and you won't find that now because modern systems now have what we call preemptive control over the runtimes. And what does that mean? Well, it means it ensures all programs are given regular time on the CPU. Because the schedule will say, right, you've had your time, let's move over to the next part. And it'll say, right, you've had your time, let's move over to the next one. And in a single user operating system, maybe cooperative multitasking is all right, but even though we don't really want that, we really do want some sort of preemptive multitasking. Even though home computers generally run a smaller number of well-tested programs, that's changing as well. Windows NT, which was originally targeted to the professionals and servers, was the first version of Windows which enforced preemptive multitasking. And then once it got to Windows XP, that came onto the home user market. So you'll find now that most operating systems will run preemptive multitasking. And of course, it makes the systems more effective. So as we can see on the diagram here, we can first of all give a slice of the CPU, and then we can let go and let the other one have another bit of time on the CPU, and then we can finally let the third process have a bit of time on the CPU, and then it will go around the loop. But to users, because these times are so small, to users it seems that it's all happening concurrently, but it's actually slicing the time and sharing the time out between all the different processes. And of course, they all have their own priority as well. Some things may have a higher priority, so we might get more of a chance and more of a time to run things. So, there you go. Quite a lot there that we've spoken about. Hopefully now you understand some of the things that go on inside the computer. What the kernel is, how program execution is dealt with, what interrupts are, talked about memory management, virtual memory, and then multitasking.